Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will introduce the moment generating functions. These functions are very important in probability and statistical inference. But before we start talking about MGFs, moment generating functions, I will show you a definition from our textbook. Okay? This definition will help us understand why these functions we will study today are called moment generating functions. Okay? So, again, you can find this definition in our textbook, and what we have here is that they define the moment of a random variable, the kth moment of a random variable about the origin, as a particular expected value. So for instance, when k equals 1, the first moment about the origin is just the expected value of y, so just the mean. On the other hand, for instance, the second moment of the random variable y about the origin would be the expected value of y squared. Make sense? Okay, so it's just jargon. Okay, so now that we understand that term, right, now that we have been introduced to that term of a moment about the origin, okay, of a random variable, let me show you the definition of MGF, moment generating function. Again, you will find this definition in our textbook as well. So the moment generating function, as you can see from that slide, is defined as the expected value of a function. Okay, and this function, this transformation, is e to the power t times y. Okay. Well, now what we're going to be doing is now trying to understand why is e of e to the ty called the MGF, the moment generating function. Okay? So y is the expected value of e to the ty called the MGF, moment generating function. Okay? So in order to explain why this expected value is called the MGF, we will have to revisit something that we have discussed before in another video. We will revisit Maclaurin Series. Okay, so what we're going to be doing is thinking about this transformation e to the ty as a function of t, and we're going to re-express it using a Maclaurin series. Okay. So let f of t, we're thinking about that transformation as a function of t. Okay. And let's re-express it or rewrite it using Maclaurin series. Okay, there we are. So as you recall, right, we're going to need the function evaluated at 0, the first derivative evaluated at 0, second derivative evaluated at 0, third derivative, and so on, right? So first, let's find the first derivative. So first derivative, and we're thinking about this guy as a function of t, so f prime will be, e to the ty times the derivative with respect to t of that exponent. That's just the chain rule, right? So it would be y. Okay, makes sense? And it would be, let me do it like that. Okay. Now let's find the second derivative. Second derivative, f double prime, would be this guy. Y is just a constant with respect to t, right? So it's going to be the derivative of a constant times this function, but we know that the derivative of e to the ty is y times e to the ty times that y, which was constant. We end up only with y square times this, right? So makes sense? Now, as you can imagine, if we find the third derivative with respect to t, right, again it would be the derivative of a constant times this function. Constant, it's factored out of the derivative, if you will. Then the derivative of this guy would be y e to the ty. Then you end up with y cubed times e to the ty. Makes sense? And we could keep going like that. Okay? So now let me rewrite f at t, this guy, using a Maclaurin series, and I'm going to remind you what that Maclaurin series looks like in general for a function ft, right? So now what we need here is the first derivative, but evaluated at 0, right, times t. That's a variable that we are using here. Then we would have this guy, second derivative, evaluated at 0. Divided by 2 factorial times t square. And then we will have the third derivative of f with respect to t divided by 3 factorial evaluated at 0 times t cube. Remember, we're just re-expressing this function as a sum of polynomials, an infinite sum of polynomials. Okay, so in this particular case, what we have is that f of t is e to the t y. F at 0 is going to be clearly 1, right? F evaluated at 0 is just 1, plus f prime at 0 would be just f prime at 0 would be just, you know, y, right? E to the power of 0, 1 times y, okay? So t times y, f double prime at 0, right? We end up only with that constant, y square times t square divided by 2 factorial, right? So let's write it down. So it's going to be t square times y square divided by 2 factorial. Okay. Next one, something really similar, right? F triple prime at 0, we only have y cube left times t cube divided by 3 factorial, right? Oh, let me copy paste this one. And then we will have a cube here. We will have a 3 instead of a 2, 3 instead of a 2, 3 instead of a 2. Make sense? Okay. Now, let's go back to the way an MGF is defined. This guy, right, it's what we call the MGF, right? Let me be super specific that this guy, let me use a subscript to be super specific that that's the MGF of the random variable y, right? Okay, it's defined as this expected value, right? Let's find the expected value of e to the ty. So we have the expected value of a sum, right? An infinite sum. Series. So if the series is convergent, then we get to do what we're going to do here, that the expected value of a sum is the sum of expected values. Okay? So if we have a convergent series there, then the expected value of a sum is the sum of expected values, even when the sum is infinite. Okay? So now let me copy paste this guy. I just want the guys inside, okay? Let me copy paste those. Okay. Expected value of each of those terms right? Expected value of a constant, the constant itself. Now, remember that the random variable is y. So we have something that, from that perspective, t could be considered as a constant, meaning that is not the random variable, right? So you have t, expected value of y, right? And then you have something similar here for this guy. You could factor out that t square, because the expected value is taken with respect to y, right? That's the random variable. Okay. Now, as we said, right, by definition, the moment generating function is the expected value of e to the ty. So let me just say that what we have here is the MGF, by definition, the MGF of the random variable y. Okay. Now, I want you to do something here. Find the derivative with respect to t, okay, of that function, and we're going to evaluate it then at 0 and see what happens. Okay, so take the derivative with respect to t of that function. So the derivative of a constant, 0, the derivative of t times expected value of y, note that we're taking the derivative with respect to t. So this is 1 times expected value of y. Next one. Derivative of t squared, it's going to be just 2 times t times this guy. And then if you compute the derivative of t cubed, that's going to be t, well, 3 times t squared times this, because with respect to t, that is just a constant, right? Okay, so finally, let me use another notation so you can see both, right? You could write this, the first derivative of m of the random variable y at t, like this, or using prime, right? You will also encounter that notation. Okay, same thing. Anyway, just notation. Now, using that notation, what we're going to be doing is we're going to be evaluating the first derivative of the moment generating function of y at t equals 0. So if you have 2 times 0, then it's going to be 0. Then you will have 3 times 0 square, that's going to be 0, and so on. Note that the other terms, right, will also, right, if we go back to the expansion to the Maclaurin series, the other terms will have t to a higher exponent, a higher power, so t will be present in all the remaining terms, right? So when you find the derivative with respect to t, you will have here terms that involve t, right? So when you evaluate it at t equals 0, all of them will disappear. So what you have seen here is that the first derivative with respect to t of the MGF yields the expected value of the random variable, and that's why these functions, the expected value of e to the ty, right, that's why these functions are called the moment generating functions, right? Because if you do this, if you take, for instance, the second derivative with respect to t of the MGF, it turns out that you will get the expected value of y square. Give it a shot later tonight. You can easily show that the second derivative of the MGF with respect to t, that's important. The second derivative of the MGF evaluated at 0 is going to give you the expected value of y square. Okay, so that leads me to show you a theorem that you have in your textbook, but that we also have in our lecture notes. It's that theorem. Okay, and it is basically saying what we just did. So we did it for the first moment about the origin. For the expected value of y, we saw that the first derivative with respect to t of the MGF is going to give you the expected value, and here I should have a k, right, to avoid any sort of a misunderstanding. So anyway, so it's just what we said here, right? First derivative, it's going to give you the expected value of y. Second derivative, the expected value of y square. Third derivative would give you the expected value of y cubed, and so on. Make sense? Okay, so just to summarize, what we did today in this video was introducing the MGFs, right? And one of the important features of MGFs is that they give you the moments of a random variable about the origin. How? Well, all you have to do is take, for instance, if you're interested in the expected value, just take the first derivative of the MGF with respect to t, okay, and evaluate it at t equals 0, and that gives you the expected value. And you could do something similar for higher order moments about the origin. Okay, well, that's it. Thank you so much for watching. Please take care and keep working hard. Bye.